Welcome. In this video, I am going to discuss about the Fresnel diffraction at a straight edge. Okay. So before starting this video, I would request you to watch the video on the Fresnel's theory of half period zone because we are going to use some of the idea from that lecture and it will help you a lot to understand this video very easily. So just let's begin this video. Okay, so before starting that Fresnel's diffraction at a straight edge, that is the principle of that, I would like to introduce the cylindrical wavefront to you. Okay, because we need that. So suppose we have a slit. Okay, suppose we have a slit of length L, a kind of light source. Okay, so it will emit the waves in all the direction. So you can guess when this slit will spread light wave in all the direction, the shape of that wavefront will be cylindrical. You can easily guess, and it will be like this. So light propagating in all the directions, radially outward, so it will form a cylinder. Okay. Now suppose this W1 and W2 is the portion of that cylinder. And we just consider, for the analysis purpose, we will just consider an arc of this cylinder. Let's say PAQ, this arc. Okay. So this PAQ is just the equatorial section of this wavefront. Okay. So this cylindrical wavefront and PAQ is the equatorial section. Now suppose there will be any point of observation P naught, then what we will do, we will just draw a perpendicular on the slit and the position of this PAQ in the middle. So S is the middle point of this slit. Okay, P is naught is the point of observation. And I have discussed a lot of time, when you draw a perpendicular, or if you join the source point with the point of observation, then it will intersect the wavefront, and the point at which it will intersect, that point we call pole of wave with respect to that point of observation. Okay, so let's consider this arc PAQ. Now we are just dealing with that section. This P naught is the point of observation and this is the S. Okay, S point. Then we can easily say that A is the pole of wave with respect to P naught. Now, in order to find out the half period zone of this cylindrical wavefront, what we need to do, we just need to draw arc, okay, with considering P as a center and B plus lambda by 2, B plus 2 lambda by 2 as a radius. So we need to draw various arc, and if you have watched the previous two video, that is on the half period zone and zone plate, you easily appreciate this point because half period zone are separated by a distance of lambda by 2. So that's why we are drawing the arc of radius b plus lambda by 2, b plus 2 lambda by 2, and so on. So if you draw that arc, it will intersect at a point, suppose with this b plus lambda by 2. So it will intersect this cylindrical wavefront at two places, B2 and B. Okay. Probably this will be B1. I have written B2. So nevertheless. it's just a point. And similarly, if you draw the arc with the b plus 2 lambda by 2 radii, then it will intersect at C and C2. Okay. So it will be B1 and C1. So intersecting point on the PAQ is this. Now this is just the equatorial section. So if you think about the whole cylinder, then this cut point is along all the lengthwise. Okay. So if you just look at the cylinder, you will see a strip of length L with the thickness of or breadth of A to B. Or if you just think in this side, that is on the downward side, you will see A to B1. So this strip of length L and breadth AB or AB1 are called first half period zone. Similarly, the strip of length L and breadth B to C or B1 to C1 is called second half period zone for this cylindrical wavefront, and so on. Okay, so this is the first half period zone. Either this one or both are the first half period zone. This both are the second half period zone, and so on. Now we need this information, so remember it. So let's begin our topic: Fresnel diffraction at straight edge. Let's suppose this A, the point A is the straight edge of this obstacle AL. Okay, and it is placed in front of a slit. Okay, so you can think that slit is perpendicular to this screen. Similarly, this obstacle is perpendicular to this screen. So what we are seeing, just the projection. Okay, so that's why if you see the projection of a slit, and if slit is placed perpendicular to this screen, you will see only one point, and that's what we are saying, this point. And similarly for the obstacle, what we will see, a line. So this is AL obstacle, and A is the straight edge. Now as this is slit, it will a cylindrical wavefront will emerge from that. And suppose this PAQ is the equatorial section of that cylindrical wavefront. Okay, now we just place a screen to see the image. Okay, and let's assume the distance between slit and obstacle is A, distance between obstacle and screen is B. Just draw a line from the slit to point on a screen. Okay, just touching the edge. Now for the point P naught, this point A is the pole of wave. Okay, similarly if you connect any other point, suppose point P1, then R will be the pole of wave with respect to point P1. Let's join this point. Now just try to guess the intensity pattern. Okay, so let's first guess the intensity at point P0. For point P0, only the right half of the wavefront is exposed, while left half is intercepted. So if you know the Fresnel theory of half period zone, then the intensity at point P0 will be A1 by 2, sorry, amplitude A1 by 2, intensity will be square of it, where A1 is the amplitude of disturbance coming from the first half period zone. Okay. So if complete wavefront is exposed, and like in right hand side we have first, second, third, fourth till mth, so all half period zone is exposed, therefore the amplitude at the point P0 will be A1 by 2. Now if you go towards the left, that is towards the geometrical shadow, this is the geometry, so this side will be the geometrical shadow. So when you will go towards the left side, then pole of the wave shifted, okay, along this obstacle. So as a result, we first thing note, this first period zone will start from this pole. So once pole is shifted this-ward, then left side is already intercepted, but now towards the right side, as pole shifted towards the obstacle, okay, as pole shifted toward the obstacle, in the right half of the wavefront, first half period zone will be intercepted by this obstacle. Similarly, if you move further, then first two, first three, and so on. Because if you assume your pole is here, then first period zone will be somewhere here, then second, then third. But that will be intercepted by this obstacle. So once first half period zone is intercepted, then the resultant amplitude at point which is left to the P0 will be minus A2 by 2, next higher order term. Similarly, if first two will be covered, then A3 by 2. Okay. But we know that this amplitude A1, A2, A3 are in the decreasing order. So when we reach the mth term, intensity will be almost zero. So it will be cut up. So what we can guess that intensity at point P0 will be A1 by 2 square, 2 whole square, and then intensity will drop, okay, if we move left. Now think about the right hand side. Now once we will go right, what we will see that right half is already exposed, but once we will move right, this pole will move towards the R. So let's suppose we are considering we have a pole at R. So we have complete exposed right side and we have partially exposed left side. Okay. So as we gradually move, initially first half period zone will expose. Then if you move further, second half period zone will expose. If you move further, then third half period, first three half period zone will expose. So now the intensity at any point towards the right of P0 will be sum of amplitude coming from the right side as well as left side. Okay, so the illumination, suppose we are considering P1, then amplitude at this point will be sum of amplitude from the right side as well as the half period element present in this open window, that is AR. Now suppose AR contain the even number of half period zone, then the amplitude due to the even number of zone will almost zero. Why? because resultant amplitude at any point we can write A1 minus A2 plus A3 minus A4 dot dot dot. So if it is even, then and then A1 will cancel with A2, A3 cancel with A4. So it's not actually 0, but it will be much less. However, in the case when it contains odd number of elements, suppose 3, then A1 minus A2 plus A3. So A1 will cancel with A2, but we will left with A3. So the intensity will be more. So what we can guess that intensity due to or amplitude due to right hand side is always A1 by 2. But due to exposure of this left side, when we gradually move, when the even number of half period zone will expose, then it will have less intensity, but when odd number will be exposed, then we will have more intensity. So the finally we can guess that on the right of P naught we will have alternate bright and dark region. And if you see the intensity distribution, it will look like this. So this is the point where we have A1 by 2, and once we will move toward the left, we will have decreasing amplitude. Once we will move toward right, so at this maximum position, only the first half period zone in the left side is exposed. At this point, in the first minima, first and second half period zone is exposed. For the second maxima, first 3 half period zone is exposed. For the second minima, first 4 half period zone is exposed, and so on. So that's what the result is. Now just try to calculate when this situation are happening. Okay, so actually the intensity will depend upon the number of half period zone between AR, and that will depend upon the path difference AP1, okay, AP1 minus RP1. Okay. This path difference will decide how many half period zone will be contained. Okay, now just write SP1 whole square. If you think about this big triangle, then you can easily rewrite SP1 square equals to A plus B whole square plus XM whole square, where XM is the distance between P0 to P1. Remember, it will be the distance between P0 to P1. Distance between P0 to P1. Just rewrite it, take a square root, and with the assumption like x naught xm square is much this two term, then we can drop out the higher order term. Okay, now again just put back a plus b in, so we will have sp1 equals to this term. Now if sp1 is this, then rp1 we can write like this. We just need to subtract a. This is the radius of this curvature, so we need to subtract a. Similarly, if we consider this small triangle, we consider this small triangle, we can write AP1 like this. Here also we have neglected the higher order term, okay, because xm is much smaller compared to all these things, so we have neglected the higher order term. Now, what is the condition for maximum brightness at P1? Condition for maximum brightness is AR must contain odd number of zones. An odd number of zones means the odd multiple of lambda by 2. So the part difference will be odd multiple of lambda by 2. Substitute this value AP1 and RP1. We have already found that quantities. So if you substitute and if you solve it out, you will get this. And if you finally solve for xm, so this xm is the distance of mth order maximum, okay, or brightest point where we have found the maximum brightness. Similarly, for the minimum brightness, this part difference will be even multiple of lambda by 2. So it will be 2m into lambda by 2. So if you solve it out, you will get xm, which is the position of, it will be minimum brightness, sorry, it will be minimum brightness. This will not be maximum, it will be minimum. So minimum brightness is this, where 2m plus 1 is just replaced by 2m. So these are the two important conditions we know. Now let's try to find out some more quantities. So just do this. Just take xm plus 1 square minus xm square. Just find out this quantity. This quantity will be a constant. Why? Because a plus b is already fixed, lambda is fixed, so we have a constant quantity. So let's try to find out the fringe width. Fringe width will be difference between two consecutive maxima. So let's just take a difference of xm plus 1 minus xm. Now if you just think this equation, you can a minus b square term, so you can like a plus b and a minus b. Okay, it is just identity, a minus b, a square minus b square equals to a plus b into a minus b. So use that formula. So you will have this equals to xm plus 1 whole square minus xm whole square divided by xm plus 1 plus xm, and that quantity is 2k. Now if these two quantities are very nearby, okay, so we can consider that this xm plus 1 and xm from p naught is approximately at same distance, so we can rewrite it 2xm, 2 to cancel. So fringe width we can see is inversely proportional to the distance. So uh, if we move more and more toward right, fringe width will decrease. That means fringe width decrease with the increase in order number, because xm is proportional to square root of m. So fringe width gradually decrease with the increase in order number. And what else we can do from here? We can find out the wavelength of light used. So we can use this experiment to find out the wavelength. How? This is the condition for maximum brightness, okay? So if we suppose we just measure the two nth order and mth order maxima, and we just take a difference between distance like this. So if d is the distance between the nth order maxima and mth order maxima, and if you substitute this formula is like this, so you can experimentally measure the d, you can count for p, you can count for, sorry, it will be n, so you can count for n, and if you substitute in this formula, and you can easily solve for lambda because other two quantities are known. So see you in next part. Thank you.